Welcome to the course on FPGA based signal processing systems. In continuation to the Verilog introduction, we will learn a few more details about this syntaxes. So the literals which have been covered in the previous lecture, just a recap of it. This is having the usually the number specification is mentioned in this way, that is n apostrophe base for b and dt. The meaning n is the size of the bit size, and apostrophe b is the base format, and the d is the number. D represents the number which we are going to specify. So n is the decimal number size, it is especially the number of bits, and then a single letter which be the base format can be binary, octal, hexadecimal and decimal. So the default is decimal. So if the capital B is written as small b, then it is going to be a binary one, and if it's O, the number specified is octal, or if it is H, it's going to be hexadecimal, and it's D, the representation is decimal. It's a default is decimal. So the 4 bits, for example, 4-bit binary 1010 represents a 1010 binary number. B is the base format, it's of 4 bits, and the string can be 1 or more bits. The number of the bits can be anything, like the number of bits can be written in the base format. So coming to the concatenation operators. So the operator is a curly braces, the open and close curly braces. It's in continuation with the arithmetic operators what we had seen, and then the logical operators, also the bitwise operators, shift operators. The concatenation is the another operator which usually combines the 2-bit formats or the numbers here, or even they used for strings. This is the curly braces. For example, here we take this concatenation. It's a 2-bit binary 00 number and comma 2-bit binary 01. So when we try to combine this two and write it as the 4-bit binary of 001. So the first 2 bit comes from the first number, and the second 2 bits come from the second number. So we can have the multiple as well. So the 2-bit 00, 2-bit 01 are combined in this. It's a concatenated operator example, and we can even combine this byte 1, byte 2, byte 3, byte 4. The byte 1 can be of number of bits which is specified, like that is if it is an 8-bit number specified already in the program in the Verilog module. So the byte 1 is 8 bits, and then another byte 1, it is also 8 bit, byte 2 is 8 bits, and byte 3 is 8 bits. So it is 16, and then plus 16 here, 32-bit vector. It represents the 32-bit vector. It depends on the number which is specified for byte 1. So that's going to be, this is of 8 bits each. Byte 1 is 8-bit and byte 2 is also 8-bit here represented. So here then it is going to be the 32-bit vector. So we specify this variable byte 1, byte 3, and then combine them using the concatenation operator. So replication operator. So we want to repeat certain digits, now the bits of the number. For example, 0001 want to be repeated. N is the number of times you want to repeat this. So it's a replication operator. So with the concatenation operator, if you have n, the n is specified 3 times this curly braces, then 3 times this replication will occur. So for example, 2 times the byte 1 and 2 times the byte 2. So here you would get this, that is 2 into, that is 8-bit byte 1, for example, can be, that is going to be replicated, that is 16 bits, and then here 2 into byte 2, that is also byte 2 is also here 8 bits. In that case, there is 2 into 8-bit, that is going to be 16 bits. So 32-bit vector you will get. So here byte 1, byte 2, byte 3 values are not shown, but for example we took that it is going to be 8-bit. So or it can be as specified in the program, it can be a 4-bit or 2 bits or the 3 bits. So this is about the concatenation operator and the replication operator. Also the padding, if you want to do some operations like logical and or operations. So vectors are defined these two variables with different bit size. One is 2-bit, another one is 4-bit. Then the 0 padding is done at the left left bits. Okay, so if which is it makes it the both the operands of equal size bits. So in that process, the vectors are almost aligned with rightmost bit. So the leftmost bit will be taken as 0 0. So the value of 2-bit binary 0, that is 1 1. So for example, this is the first number here given here, and then the 4-bit 0 1 0 1. So this is the second one is 0 1 0 1. So the two are not in equal size. So it appends 0 0 in front of 1 1 1. That's what this padding 0 is not after this LSB. It is before the 0 0 1 1 number. So the 0 0 are appended. So this is meaning of padding here. So when you AND these two numbers, you would get this one, and this is a bitwise AND. So you have 0 0 0. So 0 0 0 1 is the output of this operation. So this is the padding with 0. So the padding zeros in the most significant bits will be replaced with this zeros. Then we come to this. With this, we have this number specification we have seen. Also the modules which is having the declaration and statements, how the module are instantiated in the another module of a Verilog. If we have the top level module and then lower level module, multiple instantiations are possible. Number specifications, negative numbers, how they are going to be represented. Okay, so those things we have seen. So apart from that, we specify this. There are two classes of signals that is in the Verilog. So those are, one is nets and another one is variables. So these are the two important class of signals need to be known when you write the Verilog code. So the first one is that net. Nets are roughly, there are wires that is in the physical circuit. So for example, if you have an AND gate and the inputs A, B and C, so these A, B and C can be represented as the wires, and C can be even ANDed with or R with D to give an output E. So in this, the lines which we have, the inputs and the outputs of these gates can be represented these are the wires. So these wires can be represented with nets. So that is, these are the nets can be of different types. What are the net types available in the Verilog? We'll see. One type of signal is that net. So this is a physical circuit, and connecting this, again, this provides a connectivity between the elements. That is one thing. Also the modules, especially in the structural modeling, we are going to look at the structural modeling and the data flow modeling, and also the behavioral modeling of the digital circuits. So in that, we'd be able to figure out what is this exactly. The wire is, it's just a basic connectivity which it provides between the elements. It's a wire. So the net, the input output ports, that is, we say that here is an input. In the Verilog module, we specify input port as well as the output ports. The input and output ports are often nets. So these are wires. Then where it can be wire, where it cannot be, so these details we will be looking at. Right now the understanding is this input output ports can be nets, and this wire is a default net type. That is, any signal which we have declared in the module. We have seen in the previous lecture the one example of module, N module, and then there is a module name and there is a port names. So the port names are specified. Suppose this A, B, D are specified, A, B, D and E. A, B and D are inputs. In the declaration section, we write that the inputs are A, B and D and the output is E. That's the declaration part. So if you don't define any of this nets, the input ports which are mentioned in the port name list, the list of port names, and not declared in the declaration section, would be considered as wires, or which type of it is, which type of net it is. If we don't define it, then the signal name that is going to be considered as the wires. So this is about, we will be seeing many more examples about how these wires are. So net is actually, again, the different net types are available. This is one signal type which is net. And if we take the different net types, wire is one net type, and then wire AND is another net type. Also wire R is net type. Tri, TRI, these are all keywords or the reserved words. Dry and is also net type. Try or, try register, and then try 0, try 1, and supply 0, supply 1. So these are Verilog net types. So the totally Verilog net types, so commonly used are wire and try. Okay, so let's see how this wire and net declarations usually done in the program. So the wire is wire, we say this, suppose ABD, in that case, in the previous example, AB and D, ABC and DE. So in that case, the example, so wire, we can say it is the identifiers or the which are declared and in the input output ports can be of identifier. So the identifier can be comma separated in the declaration. So in the declaration section, apart from the input and output declaration, the sum of the signals can be defined as wires. Okay, and this wires can be multi-bit vectors also. So for example, that is LS bit giving the range, bit range. Suppose it's going to be an 8-bit, that AND gate which accepts two inputs of 8 bits, then output would also be of 8-bit. So that C can be of 0 to 7 in that case. So this is a multi-bit vector. The identifiers can be comma separated. So if we say once the multi-bit identifiers, suppose this is A, B and C, all of them are 8 bits. So then it's possible to define or the declarations are wires with multi-bit or single bit. Also the try, which is also very common, is that identifiers can be declared as identifier 1, 2, 3 as shown here. Also the try can be multi-bit also, 0 to 7 or 7 to 0 or 16 bits, 0 to 15 or 32 bits, 0 to 31, it can be identified. So the wire, which is simply giving the connectivity, it's a physical connection, can we say. So in this try, it will try, if we suppose declare something as a try, then it is driven by multiple signals or multiple drivers are there. So for example, we can take a buffer. This is a tri-state buffer 0, or this is going to be, sorry. So these are the two signals which we have, and we can have this select line as 1 and this is x1 and x2. So we connect both of this as a single line. So here is the line, the one which is shown over here, the select line. So if select is 0, then this will be enabled and passing this signal F. If select is 1, this buffer would pass this x2 to here, and this F is driven by both of this output buffers. Okay, so in that case, this can go to high impedance state also when this buffer is not in state. So if it is 1, in that case, this buffer will be off, so it doesn't pass x1 to F. So in that case, the output goes to high impedance state. So the F in the declaration section can have this try. So it is basically driven by multiple signals or the multiple drivers. For example, here buffer 1 and buffer 2 outputs. Also, if you say wire and, again the wire and configuration of the basic signals, that is declared as wires. Declared as wires, suppose in a circuit, so for example in the previous case ABCC, and we said that is and wire. So this wire can be of multiple wires connecting the elements. So those elements forming AND logic. So that will be looking at the truth table of this wire AND function and try AND function, both will be same. AND logic, which is simply forming the AND configurations between the signals which are defined as wires, and here AND logic, which are AND logic configuration, again it is forming among the F or the try signals or the multiple drivers, the signal which is driven by multiple also can be have the tri-AND. So similarly, tri-OR, it forms the OR configuration of the multiple drivers configurations, and also this is simply OR configuration between the wires which are declared in the, if you say some signal is WOR, that's wire OR configuration with the multiple signals which we declared as wires. So the wire can be specified in the program. So we'll take out the examples on these cases. Also the tri register, which can store the charged values. Also the tri 0 and tri 1, which is again the multiple drivers, which is pull up resistors and resistive pull ups and pull downs of the devices. So it can be of a pull down, and this is pull up, this is tri 0 and tri 1. Also the supply 0, what we have, supply 0 and supply 1 can give this logic 0 and logic 1, logic 1 to the signal, or the one which is declared as, suppose a C in the previous example, if we permanently connected to supply 0, it is grounded supply 0, or if the particular wire is connected to supply 1, or declaring that as a supply 1, meaning it is of logic 1. So these are the net types. In your digital circuit, we can use the net types to declare the signals or the wires which are connected in the digital circuit. So the commonly used is wire and tri. So we will be concentrating more on these. So the next one is this variable declaration. So there are two types of signals in Verilog. One is net, another one is variable declaration. So variable declaration, if we say within the procedural code or in the behavioral description, is especially, that is a one higher level abstraction, in that we define these variables, and suppose x equal to, x is a reg, it's a register. So these identifiers which are declared in the input output ports in the behavioral description, those can be of, this is the syntax of the variable declaration. So identifier can be comma separated, and a single line register reg is again, it can be a multi-bit also. The multi-bit one has example, this LSB to MSB needs to be specified. It is which type of bits are, and how many number of bits are there in the identifiers. Also the integer declaration is also a part of the variable declaration. So the integers is some numbers, we want to iterate it for a multiple times. So we declare that as, suppose the I is especially in for loops, we have this I equal to varying from 0 to 31 or 0 to 15. So we make this, declare them I as integers. So this is a variable declaration. So variable declarations, especially reg and integers, are the, so here reg doesn't mean the register, or it is stored like a physical register. So it stores the value, the variable stores the value within the procedural code or the behavioral description. That value can change. Okay, so this is the register. Reg implies that here it is a register. So the Verilog vectors. So if we take the vectors are the multi-bit, we have this byte 1, byte 2, byte 3. Here we can declare them as registers which can store the value, that is 0 to 7. The 8-bit, byte 1 is 8-bit and byte 2 is 8-bit and byte 3 is 8-bit register. So this can be a multi-bit vector, we say this is vector. And the word 1, word 2 also, it's going to be a 16-bit register here. For example, word 1 is, if you write it in a comma separated line, so it's going to be a 16-bit. The 16-bit is valid for word 1 and word 2 as well. So this is a variable declaration, especially the register reg declaration. And ZBus, it's a variable name which is 1 to 16. Okay, so the 16 bits are defined in this way as well. So 1 to 16. So that it is a 16-bit vector. So we can select the part of this, how to select a particular. So suppose the byte 1 is defined here as 8 bits. So from the 8 bit you extract the, if you say this index 7, so that's going to be 8th bit, byte 8 bit of this byte 1 will be extracted. So if you want to select a particular bit, you can use this with a square bracket of the variable name, byte 1 7th bit. So ZBus 16-bit. So for example, so this is 16-bit, the 16th bit will be extracted from the ZBus value. So that it has the 16 bits number. The Z bus is going to be 16-bit number here. So which is a 16th bit can be extracted from that. So it is from 1 to 16 only. So it is not from 0 to 15. So it is again the 16, whatever this, the place of 16 will be extracted here. So apart the comparing this net and variable declarations, so input and in-out ports. So input is going to be the input to the digital circuit, and in-out ports can be an output, and which can be an input to other modules. So this cannot be have this variable type, that is it cannot have a reg type. So reg has to be driven by something. So here input is not driven by something here, and in-out port is also is not driven by something. So because it has an input, it can be an input also. So this can be net type as wire. So we need to differentiate between this wire declaration and reg declaration. So if we can get the reg declaration is a variable declaration, so this can be in the within the code and within the procedural code of the Verilog. So this cannot have these inputs cannot be of variable declaration or the reg one. It can be of wire. Simple net type is wire, but output ports can be either net or reg. It can be a wire or it can be reg type. So the output will be always driven by something. So the outputs always is declared as reg or net type also, and if it is needed, the output is connected to other elements, so then it is going to be a simple net, that's a wire. So when we say net type declarations, wire, wire and, wire or, try and try 0, try 1 and all of this comes into picture. When we say variable declaration, it is going to be a reg type or the integer type. So it can drive input and in-out ports of the other modules. So the output ports can drive the input and in-out ports. So that is also of the other modules, it can drive. So this can be of reg type or the net type here. So this is the distinction between this wire and the reg declaration. So let's say take some example of this, how this nets or reg declarations have been done. So the net, if we consider this B, C and A, we say the net represents this connection between the hardware elements or a basic connectivity it provides, or it's going to be simply a wire. So the wire A, the declaration can be this A can be wire A. So net A in the circuit, this can be a wire A, or wire B and C. This can also be, two of them can be wire B comma C. This is how in the declaration section it is mentioned. Also wire D, that's going to be D is not in the circuit anyway, but the variable D can be given as this 1 apostrophe B0. So that means 1 bit 0. So D is assumed here. If you declare wire D equal to 1 bit 0, you are giving this 0 value, logic value to the D. So it's a fixed value. And coming to the registers, the register can be of data storage elements. It is not, it retains the value, that is a previous value. When you say reg, it is not a physical register, or no hardware registers in this. So when we declare reg reset, it is going to be a variable reset. The variable is reset here, that can hold some value, and the initial is again the keyword initial, which executes only 1. So to it's a behavioral description. So begin and end, if you have within the behavioral description, if you have multiple statements, the block is to be written in with the begin and end. So you have two statements here in this code. So reset, now it's made as 1 bit binary 1. So initializing this reset with one value, and reset after, you can notice that there is a hash and 100. So that means the hash and hash 100 meaning the time unit. So 100 time units, that reset equal to 1 bit 0. So initially, once that reset, when the initial is executed, it made this reset value as 1 in this code, and that is initializing the reset to 1. After 100 time units, that reset is becoming 0. So we can change this reset variable to 0. So that's what is deasserted, so from 1 to 0. a small snippet of this Verilog here to say that register. So the register is reset is, you can see they declare that's register. So that can change value within the procedural description or the behavioral description here. So signed register declaration. So signed, how the register values can be, register can take values of signed also. So it is the M is the variable that is 0 to 63, that is 64 bits signed value. It can store 64 bit signed value if you declare reg, the M as reg with signed. Also I is a variable integer, specify this integer I. So in the declaration section you want that integer to be integer I. So if we coming to the vectors, so the net or the reg data types can be declared as either single bit or a multi-bit vectors. Then if we say wire A, that is going to be, we are not specifying any bit, that we had seen already also. So it's going to be a single bit or a scalar variable. If we say wire 0 to 7 bus, the bus is a variable here, it is going to be an 8 bit. So default is scalar 1 bit, and wire, if A, bus A, bus B, bus C, there are 3 of them, which says it's a 32 bit. So these 3 buses of width 32 bit. So wire can be wire or reg. So net type or reg or variable declaration. So these data types can be a single bit or a multi-bit vector, or scalar or vector of bits specified, multi-bit bits. Also the clock, it's going to be a register here. If it is defined reg clock, then it's a scalar register by default. Virtual address, so the underscore can also be used to for introducing the clarity in the variable. So variable representation, virtual underscore address, it's a vector, the virtual address of 41 bits, that it is declared as register, then it has 41 bits. So how to do the vector part select? So in this case, the example which the vector which is bus A 7, if you write, it is going to pick up the 8th bit from the bus A, and if you want to select the bits out of 8 bits or the whatever the bus A size is, it can be a 16 bit or the 0 to 2. That means it will pick up, suppose let us assume that bus is 8 bit 1010 1110. So 8 bit here from 0 to 2, 0, 1, 2. So these 3 bits will be extracted from the bus. So this is the least significant bits of 3 will be extracted from the vector bus. So virtual address 0 to 1, similarly if the virtual address is 42 bits, in that then 41 bits it is going to be extracting 0 and 1 first 2 bits from the virtual address. Also the integer, real and the time register data types. If you say something is integer and it is going to, the variable is taking only integer values, we take this initial as is again the initial to the behavioral description. The counter is equal to -1. It stores the negative values, it's -1. And if we say something is real, the data, it takes the real values, the delta is real value here. Initial, again make this begin. So for the delta now is defined as 4e10, in the sense it can take 4 into 10 power 10, that exponent of operation. So 4e10, it is given the scientific notation, and the delta now again changed to 2.13 some value, that is the previous value is replaced with the 4e10 is replaced with 2.13. That means inside the initial block this is sequential anyway, so sequentially executed. So these things we will discuss later. And in this block, so if you say delta value, now it's a real delta, because it is specified as real delta, this exponent values can be taken and 2.13 can be taken, assigned here. So then integer I is defined to be integer. If we say I is equal to delta, so in this case what happens to the delta value? So delta value was 2.3 at the end of this code, the execution, and then delta now is defined as 2.13, given as 2.13, and it is assigned to I here. So then because this I is an integer, it won't take 2.13, the I will be 2 only, that is rounded value 2 it would be assigned. So the delta, even though the delta is defined as real, but the integer value I is an integer, so it can take only the integer part of it. So for specifying the time, the time is a keyword again. Save simulation time. If you want to, when we run the simulation, if you want to save the time of the simulation, so this is the variable declared as a time. We can have this initial save time. This variable is $time. So if you say $time, then with semicolon, it saves the current simulation time in the save sim time variable. So we had seen some of the syntaxes, nets and variable declaration in this lecture. Also how the literals and numbers can be specified, different types of net types with the details we will cover it in the structural modeling, complete the wire and wire or truth tables and everything. Also the time declaration, the real, integer, reg declaration, what is the difference between this reg and wire declaration. Then the wire comes under the net declaration, whereas the reg and integer comes under the variable declaration. So these details have been covered in this lecture. Thank you.